Good afternoon, everyone. So today, as already mentioned by Arya, we'll be mostly talking about glacier-related hazards, concentrating mostly on glacial lake outburst floods. So here in this talk, I would take examples of past events and also look into anticipated future events. Uh, with that, these are my contents of the presentation, where I'll be talking about the global temperature changes, its impact on glacial lakes, glacial lake outburst flood modeling, hazard assessments, how modeling techniques can be used to design early warning systems for outburst floods, and also look into a little bit towards GLOF mitigation and how modeling techniques can be used uh, to model GLOF mitigation and look into future prospects. So before I start my talk, this is the video that I would like to play, since I would be talking uh, about glacial lake outburst flood. I would like all of you to see about the I'd like to show this video where uh, we all can have a look how what is the magnitude I'll be talking about for the rest of the talk, or these floods can be. So that tells you about the magnitude and how destructive these glacial lake outburst floods can be, and can wash away downstream villages, destroy infrastructure, also impact human lives. The video that I just played was from the Kedarnath event that occurred in the year 2013. These are some of the images on the right, where you can see the settlement at Kedarnath before the flood event in November 2011. We could see a lot of new settlements have grown from 1960. If you compare the settlements in 1965, we could see a lot of new settlements, and this was the limit in 1965. And this is a post-flood image where you can see that most of the uh, settlements where buildings and infrastructures were destroyed and washed away during the flood. Uh, these were categorized. If you see the categories, only the red color represents the buildings that were totally destructed. The yellow representing the one that those were partially destroyed, and only the green parts, green buildings or infrastructure that remained intact after the flood. Well, in this talk, what I want, why I want to show you these schematic diagrams is that we need to understand how cryosphere is basically uh, connected to the other spheres of the globe. Here, mostly in this talk, we will be mostly concentrating on the connection between the cryosphere and the lithosphere, and also the cryosphere and the anthroposphere when it comes to processes, mechanisms, and changes that is occurring in the cryosphere, and its a relation with the lithosphere, where we will be learning or talking about surface processes or different disasters that may originate in the cryosphere and interact with the lithosphere. Whereas in anthroposphere, we see the impacts and adaptations where it's the normal people are involved, human beings are involved, and how uh, the impacts and adaptation to such cryohazards and disasters can be dealt with. So when I talk about lithosphere and connection to cryosphere, we can it can be in a way that the land processes can be quantified. For example, when we are talking about glacier-related hazards, we are talking about ice avalanches, glacial lake outbursts, floods, rock ice avalanche, and so on. So this connection can be uh, built by using different scientific ways to quantify these potential events. And also when it comes to real implementation of risk management and future sustainability, and also looking into adaptations, we can see how cryosphere can be connected to the enterosphere. So this is what motivates me every time when I'm talking about such glacier-related hazards. If you see the global temperature trends over the years from 1980s to 2015, you could see the temperature anomaly around the globe. Uh, Temperature rising, is rising every year. This is shown as a temporal interval of 5 years. In the recent IPCC AR assessment report 6, what we could see that um, on the right, if you see the temperature trends till 1850s, it was quite stable, but after 1850s, we could see that the temperatures are rising high with an anomaly of over 1 degrees now. And then if you see it closely from 1850s to present, we could see that this is the observed temperature trend, and the temperature anomaly has rose over, I think, over a degree now. So if you look into the modeling results presented in the IPCC assessment report 6 from 1950s, you can see that the temperatures can go high up to 4 degrees if there is no cut in the emissions and greenhouse gases. So that is a real concern when we are talking about such high mountain hazards, because these temperature changes are directly or indirectly impacting the glaciers at high altitude and the water towers, in a way impacting the water availability downstream, also negatively impacting uh, in terms of risk and hazards associated with these kind of events. This is an important schematic which I really like, is because that we will be talking mostly on the glacier hazards here, but this whole schematic tells that the atmospheric drivers, which are normally the temperature, uh, precipitation, humidity, etc., is playing a major role here, which is changing the mountain cryosphere, which includes glaciers, snow cover, permafrost, lakes, river ice, etc., and eventually leading to such hazards related to the cryosphere and impacting the livelihood and human mobility, tourism, etc. So we could see that the atmospheric drivers are sitting on the top. So this is directly impacting all of it. So this is a periglacial environment, which shows how these high glacier-related hazards can be classified. Here we have the periglacial debris flow, which can be in the form of a rockfall, it can be in the form of an ice avalanche, or it can be also in a form of a moraine dam lake failure, which causes glacial lake outburst flood impacting downstream region. A very interesting paper which was published last year, which documented about quantified the changes in the glacial lakes overall in the globe from 1990s. And what was interestingly found is that the global glacier lake volume has increased by 48% and between 1990s and 2018. And yes, of course, over this study period, the lake number and the total area also increased by 53 and 51% respectively. That is almost, it is all more than double than what we had in 1990s. So you can see how the cryosphere has been changing, how these glacial lakes have been evolving and formation of new lakes over the time. And this is what concerns us when it comes to high mountain hazards, as these newly formed lakes can be risky to the downstream regions. This is also a benchmark paper published in the journal Science, where it is seen that most of the glaciers, benchmark glaciers in eastern, central, and western Himalaya are showing negative length changes. That is, they are losing mass and retreating over the years uh, from 1840s to 2020. Yes, of course. This is also what is responsible for such glacial uh, dynamics that is happening at an altitude, say around 4,000 meters above mean sea level. As these glaciers retreat, the meltwater is being trapped at different by damming materials, and the lakes are formed. There was another important paper which was published which says unchanged frequency of moraine dam glacial lake outburst floods. So what does this mean? This says that the frequency hasn't changed, but yes, of course. How about the magnitudes? Is it that the magnitudes are changing over the years? As this paper says, as these are important concerns to look into the magnitude of the events. So when you look into the Himalayas, there are around 25,000 glacial lakes spread across the Indus, Ganga, and Brahmaputra river valleys. These glacial lakes are normally formed when you have a glaciarized body, and with time, as the glacier retreats, the meltwater from the glacial lake is stored, which is dammed by a frontal dam, which is normally composed of glacier deposits called tillites or moraines. And this is an example satellite image showing how these lakes can be monitored using remote sensing. Image in 1994, and in 2016 you can see the change in the lake area when mapped using Landsat satellite imageries. Other examples here, of course, can be supraglacial lakes, which the lakes that form on top of the glaciers. Here's a timeline of from 1968 to 2016. We could see how small glacial lakes have combined together to form larger glacial lakes. So these glacial lakes can be, of course, monitored using remote sensing techniques and GIS techniques, and temporarily mapped. And this is how this is an area in Sikkim where you can see these glacial lakes and how GIS techniques can be used to identify the boundaries of such lakes. Let us take an example here to look into the lake inventory in the state of Uttarakhand from 1968 to 2016. So there were around 60 glacial lakes that were mapped in 1968 using historical satellite images like Corona, and then 27 new lakes formed by 1994, the total number becoming 87. And then here again, by 2001, we have around 102 lakes, and then finally 828 more lakes formed with a total of 130 lakes in Uttarakhand. So we could see how these lakes in Uttarakhand, especially state located in the central Himalaya, the lake area has been growing. Now, if we look into the different basins, sub-basins of different river basins in Uttarakhand, we can see that majority of the glacial lakes are present in the Bhagirathi and the Alaknanda basin. And if you see the temporal changes from 1968 to 2016, we could see that the maximum change also occurred in these two basins of Bhagirathi and Alaknanda. Now, if we look into the distribution of these lakes in terms of elevation, you can see that most of these lakes are located at an elevation band of 4,500 to 5,000 meters above mean sea level, and also changes are mostly occurring are prominent in this elevation band. We can equally see that 5,500 to 5,000. This elevation also has a lot of changes occurring in these lakes. So just to show you, I'll quickly skip this slides here, just to show how satellite images can be used to monitor. Here is an image where it's a corona image from 1968 and an image from 2015. If we look closely here, we have this glacial lake that almost doubled its size in 2015 and in 1994 and 2000 respectively. And such an example again in Uttarakhand, where small glacial lakes combine together to form a larger lake and eventually forming a huge lake. But not all lakes that are present upstream or at higher elevations are hazardous. Some lakes may not grow over time. For example, these are some of the examples: Vasuki Tal, Kedar Tal, and Hemkund Tal, where you could see that over the years the lake area did not change. And this does not tell you that the hazard levels are low, but of course, this tells you that some lakes might stay stable over the years when it comes in terms of its spatial area. Let us see how glacial lake outburst process chain or the process can be represented. You can see the schematic showing the different processes that are involved in the glacial lake outburst flood, starting with an impulse wave generation, that is any mass movement that impacts the glacial lake, which can lead to wave propagation towards the frontal dam, and then there can be overtopping at the crest of the moraine, eventually leading to progressive erosion of the moraine, and then finally downstream propagation causing downstream damage. So this is where we are currently working on glacier related hazards. We are currently working on the Himalayas in the US, Peru, New Zealand, some of where I have highlighted my collaborations and also my on the projects that I have worked. And yes, of course, this completed projects and the ongoing research that I am currently involved with. In India, I'm mostly interested in looking into glacier-related hazards in the state of Jammu Kashmir, Himachal Pradesh, Uttarakhand, Sikkim, Arunachal Pradesh, and also to look into transboundary impacts of such hazards when it comes to China, Nepal, or Nepal, India. Here I would like to present one of our studies in the Sikkim Himalaya, which was funded by the Imprint project here. Here in the state of Sikkim, what we tried to do is that there were already previous lake inventories that were available by different authors, by Varni Raj Agarwal and Mool, where we tried to evaluate and review this literature available and try to evaluate only the larger lakes with over 0.3 square kilometers. And then we could see that there were 14 lakes identified. This is the state of Sikkim. You can see the lake numbers numbered from 1 to 14. These were the lakes above 0.3 square kilometers. Then we looked into the temporal changes that these lakes have undergone, and you can see that. So this is the changes in these lakes identified, the larger lakes from 1990 to 2018 again. You can see that Lake 2 here, which is identified as the South Lonart Lake, has shown a maximum change over the years. And if you look into the previous inventories and susceptibility outburst, glacial lake outburst probability and susceptibility analysis, we could see that Lake 2 has been identified at high bluff susceptibility by other authors as well. It was identified as potentially dangerous by Raj et al. In 2013. So yes, this was a concern where the South Lonark Lake was growing over the years at a rapid rate. And sorry, this is now published. This is still in review. I've written. So soon after that, I saw this news in Sikkim Express, where they said early warning system is to be installed for this South Lonark Lake. So here you could see that there were some efforts where siphons were installed in the lake, where temporary drainage of the lake led to lake surface reduction in order to reduce the hazard levels of the lake. Following that, we tried to look into the flow dynamics and the flow hydraulics in case of a future potential flood from this lake, originating from this lake, and what impact it would have in the downstream region. For example, a major settlement uh, located downstream, which is called Chungtang here. Here you could see this is the location of the lake. These are two settlements, Lachin and Chungtang. On the right here, this is the settlement as Chungtang. You can see in 2016 there was no hydropower station which was located, and in 2019 we could see that hydropower construction initiated, and 2013 the hydropower construction was under construction, and then by 2016 and 2020 we have a full-fledged hydropower station in operation. We can see the reservoir here, where and the settlement, if you look in closely into the settlement pattern from 2016 to 2020, we can see that there's a lot of new infrastructures and buildings that were built over these years. So this implies that in case of a potential future flood event can hugely impact uh, the Chungthang village, because many of the settlements are constructed along the shore of the main flow channel from the South Lonark Lake. And yes, of course, since the infrastructure have changed over the years, the exposure levels have also changed. So this was the sonar-based bathymetry, the depth, spatially distributed depth of the South Lonark Lake, which was published in 2018 by Sharma et al. Uh, we constructed a 3D GIS model of the South Lonark Lake, incorporating the total volume that was measured in the field of 65 million cubic meters, and then numerical hydrodynamic model was implemented to see what kind of an impact the downstream would have in case of different scenario, which is called scenario-based dam breach modeling. Here we considered four different scenarios, scenario 1, 2, 3, and 4, where scenario 1 and 2 represented overtopping mode of failure, whereas 3 and 4 uh, basically represented piping mode of failure. What is the basic difference is that piping failures generally can start from any point of the moraine, maybe due to internal failure of the moraine. But in case of overtopping failures, the water from the lake overtops the frontal moraine and overflows the frontal moraine, leading to progressive erosion, initiating erosion at the crest of the moraine, and then finally uh, progressing towards the base of the moraine, leading to the complete or partial drainage of the lake catastrophically. So these are some of the inputs that we use for the model, where we use the land use, land cover from the source to the place of Chungtang, different land use categories for the channel roughness to determine this channel roughness and the flow. What we could see that in case of among the four different scenarios that were modeled, we could see that overtopping model, the worst case overtopping failure would cause a flood that would have a peak of 6,000 cumex, and as the flow moves down and reaches Chungtang, the peak is calculated or determined to be around 3,823 cubics at Chungthang. So what was interesting that we saw is that at around 6 kilometers downstream from the lake, we could see that there was a major flow obstruction to the Gulf, the potential Gulf, and we could see the flood was redirected towards a smaller passage, and then it opened up as it passed on, and this severely affected the Gulf hydraulics, as if you can see the changes in the flow hydraulics. So this is location A and location B. This is upstream and this is the flow direction. And you can see this is the obstruction where a 90-meter high obstruction, and the flow was redirected. And you can see the flow velocity almost reduced by half, from 8 meters per second to 4 meters per second from location A to location B, whereas water depth, yes, of course, have reduced here from 16 meters to around 3 meters when you compare location A and location B. Yes, of course, high water depth at location A is due to the sudden blockage of water here. And if we look into the impact of such a Gulf in the village Chungthang, you could see that majority of the settlements in Chungthang is inundated, where flow depths can go up to 8 meters and 4 meters at places, and then the flow velocity may be around 4.5 meters per second to 9 meters per second. So this was the inundation hazards and the potential impact on Chungthang, but there were a few questions that were still remaining to be answered. One was, what would be the extent of the South Lonark Lake in the future, and what are the next questions to be addressed in a way that what would be the future Gulf triggers? What can trigger a Gulf in case of South Lonark Lake? What are the uncertainties involved when you're modeling Gulf and characterizing this? And is there an early warning system that is required for this lake? Following that, we published a paper in geomorphology where we looked into the future hazard potential of this lake. Again, for this year, we tried to look into different scenarios of the future. For initially, the future volume of the lake was identified, and then was followed by identification of the avalanche or mass movement sources around the lake, which can basically trigger a Gulf event. That was also was studied for 3 different scenarios, where an avalanche of 5 meters or 30 meters or 50 meters would descend down the slope and impact the lake. And if there was an impact wave, the impact wave was characterized using an overtopping model. And if there was overtopping, yes, of course, then it was used to see the hazard downstream using different dam breach scenarios, where we considered 30 meters, 35 meters, and 40-meter breach events. And finally, we calculated the uncertainty of such Gulf modeling using a lower limit and an upper limit to the breach dimensions, and of course the predicted breach parameters that includes the breach width and the breach formation time. So just to show you how glacial lakes are basically growing, this is how it grows, and once the glacier recedes in the future, you can see that the glacial lake have grown newly. The bed has been newly exposed. There is glacier thinning, and what happens as the glacier recedes, the lake is getting exposed to the surrounding slopes, which can be sources of avalanches or rockfalls in the future, and that can trigger a Gulf event in the future. So important point here is that currently the glacial lake might not be hazardous, but the hazard potential can of course change over the time if the glacier changes or it grows and approaches the potentially unstable slopes around. So these were some of the ice thickness results that were used to validate to calculate the over deepening for different shape factors and an ensemble ice thickness to if you were compared, and this is how the green color here is the bathymetry of the lake, and it was validated with the real bathymetry, and we could see that the ensemble ice thickness matched really well with an RMSE of I do not remember the RMCB, but the difference of less than 20%, of course. And then we use this ice thickness to calculate the glacier bed and the over deepening site, and we could see that the future, this is how the lake would evolve from 1990s to 2019 is what we know, and this would be the future extent, almost double in size than what we have today. And different modeling flow depths are at 20 meters, 30 meters, and 40 meters. And these are some of the overtopping modeling results where you could see that 3 different scenarios of rock ice avalanche or a snow avalanche were considered, what different volumes released from the side slope. And we could see that at scenario 3 with almost a volume of 3 million cubic meters of snow falls onto the lake can have an impact onto the lake, which can lead to overtopping. Here, if you see the overtopping modeling can lead to overtopping of a wave height up to 3.7 meters, which means that in case of an avalanche of 3 million cubic meters can initiate erosion at the dam crest, right? So this is the source. If you look into avalanche source, if you look into the Google Earth imagery closely, you have a lot of crevasses, hanging ice, and of course the future glacial lake approaching this slope. These are some of the results of future hazard assessment of the South Lanark Lake and the uncertainty. I could see that there can be at Chungthang there can be flood up to 6,000 cumex, and the gray color bars here gives you the uncertainty where 3 different model results are represented here. One is the lower limit, upper limit, and the predicted. So this is how you can basically look into the sensitivity of these models by looking into different parameters, especially breach parameters when it comes to time of failure and breach width. Here, one of the papers that was articles that was published in 2019, where we looked into the sensitivity of such hydrodynamic models to breach parameters. Here you can see clearly see that the model is highly sensitive to time of failure than the breach width. Yes, of course. So it is highly important that such parameters are carefully determined, because these can lead to great changes in the final output. So this is at Chungthang. You can see that I'll just quickly skip here. You can see on the right in the future that most of the buildings along the Chungthang are exposed. Many industries, for example, the bridges, the hydropower industry are at high risk. And this is the flow intensity map, which is a function of the flow depth and the flow velocity. Velocity categorized into low, moderate, and more and high and extreme. You can see that in a 40-meter breach, almost the entire Chungthang village is at high intensity zones. So the major findings that I would like to highlight here is that the Chungthang town would have 4 hours of warning time in case of a worst case glove that would happen in the future in the South Lanark Lake, that can inundate 5 major bridges which falls on the way on top of the flow channel. It can majorly impact a highway that is located at Chungthang. it can inundate a total settlement or area of 55,000 meters square. So that is why it is important to look into the potential of such glacial lakes and the impact that they can have in the downstream. So if you look into the recommendations made in order to construct an early warning system, you can see that the different warning times available at if the sensors are placed at different uh, distances from the lake, and if it is in Chungthang, if a lake is an early warning system uh, is installed right at the base of the moraine of the lake, Chungthang would have say around 4 hours of warning time. But yes, of course, it would have just 7.5 minutes, 12.5 kilometers downstream of the lake. So now I still have 20 minutes to speak. I would like to come to another study that we did. This is actually very interesting in a way that this is the deepest known lake in the Himalaya, glacier origin lake so far. Yes, of course, there can be other deep lakes, but so far as Himalaya has a very few lakes where bathymetry and surveys have been done, this is one of the known bathymetries where uh, is known to be the deepest now. So it is located in the state of Nepal. Here you can see this is the lower Barun Lake, and this is the flow channel of the lake, uh, and it has several sites. There's this Barun Bazar site 1 to site 5, where you have either minor settlements or you have infrastructure which is being exposed, which is currently being potentially exposed to a glove that might originate from this lower Barun Lake. So we tried to look into that carefully. So field investigations shows that there has been retreating terminus, formation of new supraglacial lakes, which is a signature of glacier thinning and of course lowering and receding. And yes, of course, we could also see that there was a very steep ice cliff right in front of the lake, which can be sources of potential triggers. Bathymetric surveys were done to determine the lake volume and the depth spatially distributed. And for your scale, you can see how big the Lower Barun Glacier terminus is. If this is the boat here with uh, Professor Jeffrey Cargill, and you can see that even a calving activity from this glacier front can lead to displacement of uh, the lake water. So now this region was also important if we look into the past. This was an event that occurred in the same valley. We are looking into this lake right now, which is called the Lower Barun Lake. I will point this out in the next figure. This is where we are interested to study. But yes, of course, there was an event that occurred in 2017, right in the same valley, which is called the Langmale Lake, that was because of a rock fall. You can see on the right, the rock detached from the slope here and impacted the Langmale glacial lake, which led to severe destruction downstream along this channel where Lower Barun Lake is currently located. And so this is Yangla, Karka, and Langmale is here. So you can see how the glove have impacted this valley. So that was how it was important to also evaluate the hazard assessment of Lower Barun, since the Lower Barun is much larger than the Langmale Glacial Lake. So for here, what we try to do is, of course, to look into the future volume. I'll not go into detail about how we calculated the future lake volume. It is exactly the same method using an ice thickness approach. And the avalanche modeling here, very interestingly, is based on previous events that was captured in the field. I would show you a few slides. It's surprising to know that um, this is a slide where you can see that at a time scale, of it. You can see the time here. It is 7:03 a.m. on the 24th of October 2016. You can see a dust of cloud, snow dust coming down from the slope, and this is where the Lower Barun Lake is located. This was captured when Professor Jeff was in the field, and he captured it right from his tent, and he could see that there was a snow cloud that was descending down from the slope, and he created a GIF. He immediately took out his camera, and he was lucky enough to capture this event here, where you could see that the huge ice snow avalanche fell onto the lake, impacting the lake. Luckily, there was no
Hello.
there was,
Yeah.
yes.
No. In between your voice got cut. So you can proceed. No problem.
Yeah. So luckily there was no failure of this of lake, of course. But what we wanted to see in this paper is that what if a higher magnitude event occurs from the same slope? Of course, that can have an impact on this lake. So what we tried to do is we constructed the future glacial lake bathymetry using ice thickness approach here, and then constructing the lower Barun glacier bed. Then we tried to model high magnitude events from the same slopes from where this particular event occurred, that is from Avalanche 1. And also we saw that, what if there can be another potential source, which can be Avalanche 2. So we tried to model two different avalanches of a higher magnitude that was witnessed in the field. How do we know that we have actually modeled a higher magnitude event? It is based on the reconstructed flow velocity from the time series image. So we know when it originated and when it reached the lake. So we know the distance, we know the time, and we can reconstruct such an event. And then we know that, okay, the reconstructed flow velocity was 27.7 meters per second. So in order for a higher magnitude event, it has to be of a higher velocity, which is again proportional to higher volume of mass falling down the slope. So we considered two avalanches of higher magnitude. We saw that there can be overtopping of 5.7 meters and 6.2 meters of flood wave from the dam. That is of course a risk here involved, and the hazard levels are of course high. So here what we try to do is now look into different dam breach scenarios. 8 different scenarios were modeled. If you can see the numbering here, from 1 to 1, 2, 3, 4 of the present lake, and 5, 6, 7, and 8 for the future lake volume. And these are nothing but the level up to which the moraine might breach, or moraine can breach in case of future event. So these are some of the flow hydrographs, GLOF hydrographs for different scenarios, different breach widths, different breach timing, and you can see that how from scenario 1 to scenario 4, we have larger scenarios here. As we come down, we have smaller breach, how the GLOF hydrograph is impacted here. Now, if we look into, this is one-dimensional hydrodynamic study, and if we look into the two-dimensional results here, what we can see that in scenario 4, we do not have much impact downstream, whereas in scenario 1, 2, and 3, we have different sites that are inundated. If you remember this slide, we have site 1 to site 5. This is what is the flow dynamics in different sites in different scenarios. And yes, of course, on the right, you can see the flow depths on these sites. If you look closely into the hydrographs, you have the discharge, flow depth, and flow velocity at different sites, different cross sections along these sites. Importantly is the inundation that these events can cause. Here we can see that these are the cross sections taken in these sites of site. This is Barun Bazar, site 1, site 2, site 3, 4, and 5. And this dot represents the location of this particular settlement. And these are the inundation limits. You can see that this particular settlement is at great risk because it can be inundated by either present flood or also a future flood. Whereas if you come down to site 3, here you can see that in extreme case GLOF, the inundation can be much high. But if you go down in low magnitude potential GLOFs, we can see that the inundation is relatively small, and so would be the damage would be low here. Similarly, at site 5, we can see how these can change, and in moderate potential GLOFs and low potential, these GLOF might not even reach these sites, which is site 5. So that is all for Sikkim. Now I think I'd like to a little bit talk on Jammu and Kashmir, where this was a paper where it was a reconstruction of an event of a flood that occurred in the year 2014 and had an impact on the village of the Gaya village located downstream. So if we look closely into the location here, we have the Gaya Glacier here, we have the glacial lake here, and in 2014 there was a flood that propagated downstream and impacting this Gaya village, which is located on a flat almost in the delta region of this particular flow channel. And the consequences were bad, of course. Here are different sites in the village that were destructed during the flood in 2014. You can see these bank erosion. The whole bank has been eroded. You can see several destruction of settlements, infrastructure, buildings. You can see part of the entire building was washed away. You can see deposits of boulders and inundation marks can be seen in the buildings here. And these are some of the inundation marks that were mapped in the field. So these were some of the proxies that we used to look into to reconstruct this event, taking these flood inundations as proxies to look into the modeling efforts. So these are some of the field photographs post flood. Interestingly, what we could see that on the top right, you can see that it was assumed by looking at this field investigation that the moraine might have failed by internal failure of the moraine rather than overtopping wave where the dam is eroded from the top and reaches the bottom as progressive erosion. But here it was evident that there was cracks that developed in the middle of the moraine, and eventually it enlarged and leading to increased discharge from the water moving downstream. So we tried to model this event using piping failure mode, and as we already said, we used flow heights to validate the modeling results. And here you can see that 2014 GLOF is been represented by these by this line here, the purple line, and these are some of the different scenarios we modeled using 10% potential flood volume. That is 10% of the total lake volume was drained, 20% of the total lake was drained, and 25% of the total lake drained. What we could see that and of course, yes, 30%. So what we could see that 20%, 25% of the potential volume drained during the 2014 and represented quite well with the fitting of these flow heights at different sites. And these sites are measured, are marked here. This is site 1 to 4, 5, and 6. And these are some of the modeling results for different PVFs, that is potential flood, potential volume of flood. So yes, of course, we do not know what triggered the GLOF. We tried to look into the satellite images, looked into the surrounding areas, but yes, we could not identify very thoroughly what could have triggered it. But yes, there were several potential source zones. For example, here you could see a lot of debris that was deposited here. There can be a potential source of rockfall, or there can be potential source of ice or rock avalanche that have led to mass movement into the lake, or there can be also calving activities that might have caused displacement of the wave. So this is how it would look like in case of a future event. Now that we know that only 25% of the potential flood volume have caused destruction in the village downstream. What about if the entire lake fails, and this would be the situation where majority of the Gaya village would be at potential risk. Flow depths can go up to 3 meters, 3.5 meters, and flow velocities can reach up to 15 meters in case of a future event. So I have 3 more minutes. I think I would not be able to cover the Chamoli disaster, which is again a very important event that occurred on the 7th of February. I quickly glanced through this slides so that we know what generally happened. So this is what happened in the Chamoli disaster in last year. You can see the massive flood carrying a lot of debris along with it, descended down the Ronti Gad, destructing 2 hydropower stations and causing severe damage to settlements, causing deaths, claiming human lives, etc. Huge event, but yes, this is not a glacial lake outburst flood, but instead this is a slope failure event that occurred in in the Chamoli district. Here what we have is the place where it started. It was basically a huge chunk of rock and ice that failed, leading to changes in the topography, and also changes in the rheology, also changes in its debris content, and causing severe damage to 2 hydropower stations. One is the Rainy hydropower station and the Tapovan hydropower station. So this is how it was identified. This is a 3D image where you can see where the scar representing the origin of this event, where a chunk of ice and rock descended down from an elevation of 5,600 meters above sea level, carrying huge deposits of rock, and leading to dust deposition up to several meters high from the base of the valley. You can see how these dust deposits have been seen along the channel. This is where this is the failure zone. If you look closely, you can see a triangular shaped darker zone. This is where the mass movement originated, and if you look closely, this entire part failed, descending down, and later on it converted into a hyper concentrated flow and a debris flow, causing damage. So these are the side walls. You can see how steep this entire failure zone was soon after the event. It was 180 meters maximum depth with 20 meters of ice on top of it. So basically it was a mixture of ice. It was a rock ice avalanche that have impacted the Ronti Gad. Importantly, why is it important how can these events be monitored? If you look into this Chamoli event particularly, There were precursors to this event. If you look closely into the slope, this is where this failure occurred. So you can see that if you look closely along my cursor, there was a crack that already existed. And this crack eventually widened up, and this whole block of 100 and going deep up to 180 meters failed, carrying along with it the bedrock as well as the overlying ice down to 2,500 meters. So these are some of the ways how these precursory signs can be monitored. Here you can see at two locations on this slope, particular slope A and B, the activities from 2016. You can see that there were several activities going on at these points, and point 1 and B, you can see there were movements which were precursory signs that there's movement going on and there can be potential failure of such slopes. So this is what it looked like, the failure zone with 180 meters maximum thickness, 550 meters thick, huge rock ice avalanche consisting of 80% rock and 20% ice. So other examples, other sources of information were seismic records with 3 different seismic stations where signals were received, which could be used to reconstruct the timing of the event. Here you can see the location of these hydropower seismic recording station and the source of the flood of the avalanche. So these were some of the proxies that were used to reconstruct this catastrophic event. And yes, of course, looking into some of the field evidences to know how the flow evolved as it descended down the Ronti Gad to the hydropower station in Tapovan. And there were several processes that were assumed could have happened right from an initial avalanche, fragmentation of melting of ice, splashing of mud, entrainment, erosion, deposition, and then hyperconcentrated flow and debris flow downstream. So these were again, I'm sorry, this is now published, Sugar et al. In 2021. So you can see how big this can be. If you see, this was the descending part, and this was the deposits or the sediments that were carried by this event and was deposited, also led to a formation of a temporary lake downstream, right at this location here. This is Rontegad, and we could see that a lake have formed at this due to blockage of this small outlet. And for scale, you can see how big this temporary lake is in the field. There were several deaths, of course, the victims from different states. Many local villagers were harmed during this event. And these are some of the results. So you can see erosion happening in different location as it descended down. Deposition, initial deposition, a huge chunk of deposition occurred here, and you can see how this deposition have led to the formation of new lake here. So this is based on a pre and a post event DEM, and the difference would give you how much were the changes in the terrain, whether it is addition of mass or removal of material, which gives you the erosion and deposition. And yes, since we had a lot of information to validate, starting from start time of the event, velocity of the event, inundation limits, erosion, deposition, all these could be used to successfully reconstruct this massive event. And also these were some of the videos that surfaced online soon after the event and could be used to see what time did the flood reach at a particular point. So these videos were used to look into to reconstruct this entire event. So this is how it was validated based on the different uh, times, different arrival times, which was recorded in the field, and yes, of course, which was modeled based on the evidence we have used as proxies. And here on the right, you can see the red color marks are the inundation marks, which were mapped using very high resolution post imageries, post event imageries, and two different models were used to compare the results of this. So I would like to stop here. I quickly I had more to show, but I think I'm already out of time. Um, this is a document which is the National Disaster Management Authority guidelines for management of glacial lake outburst flood. We are glad that our research has been used also in this document, which is a government document now. And for more details, you can have a look, which is available online now on the web. And these are some of the funding bodies, which I would like to definitely give my sincere thanks. And my mentors and my supervisors, I would like to thank them today. And yes, of course, thanks to the WHO Center for Climate Change, IISc Bangalore, for this opportunity. Thank you, one and all.